So, hello, Gerrit and I are going to be talking about some disputable results that have come out in the last few months from the joint analysis of BAO, CMB, and supernova data. So, as I'm sure many of you are familiar, within the last few months, DESI put out its DR2 BAO results, and they find that when jointly analyzing BAO, CMB, and supernova data, that the data have up to a 4 sigma preference for this evolving dark energy in the form of this W0 WA parameterization over a cosmological constant. And what's perhaps even more curious is that even if you drop the supernova data, the CMB and BAO data on their own still have a 3 sigma or so preference for W0 WA. And so how robust is this evidence actually? Well, something that I think is worth noting and keeping in mind and in the back of your head is that the BAO data on their own give a perfectly reasonable fit to ΛCDM, just with a slightly lower matter fraction than what is inferred from the CMB. And one way in which this slightly lower matter fraction is manifested is in the preference for a subminimal, meaning less than 60 millielectron volts, or even negative neutrino mass when jointly analyzing the primary CMB and BAO data. It's also been suggested that this discrepancy could be explained, for example, by dynamic energy, not at late times, but at much earlier times, let's say around the time of recombination or so. And it's also been shown that this discrepancy in the matter fraction can also be absorbed by a non-zero, in particular, a slightly negative curvature fraction. Okay, so with all of these different possibilities, we have a whole cosmological smorgasbord to try and explain this discrepancy that we see between the CMB and BAO data. And what we're going to dig into a little bit in this talk is whether or not this discrepancy could be explained by some kind of systematic error in the data that currently we might be sweeping under the rug. Okay, and with that, we come to the optical depth to reionization. This is the integrated free electron density all the way from the Earth back to the surface of last scattering. The optical depth is in some sense the ugly duckling of ΛCDM. And by that I mean it's, unlike the matter fraction or the primordial amplitude or, spectral tilt or so on. This is purely an astrophysical parameter that depends on the history of reionization. And the way that we infer the optical depth from CMB data is from very large scale polarization fluctuations. So during reionization, horizon size modes that have a non-zero quadrupole between the baryons and the photons produce polarization anisotropies in the same way that one produces these back at the time of last scattering. And in practice, this excess of polarization shows up at modes somewhere around L of 5 or so. Okay, so these are super large scales, and this particular shape, or this reionization bump that you get in the E mode power spectrum, is primarily sensitive to just the integrated optical depth. It's not so much dependent on the exact shape of the reionization history, as Gerrit will talk about a little bit later. Now, on these extremely large scales, the polarization from the CMB is extremely hard to measure. So, one way to emphasize this is that on these scales, the polarization signal is, less than 100 times the size of temperature fluctuations. Okay, but you still have similar or comparable levels of galactic foregrounds. Okay, and so your measurements are going to be quite sensitive to how accurately you can mask out the galaxy and trust the regions where you're not fully masking out the galaxy. as well as other instrumental effects that show up on large scales, such as nonlinearities and the analog to digital conversion. Another thing that's a little bit curious, although not necessarily indicative of systematics about the optical depth, is that over time we really only have two distinct measurements of the optical depth, one from WMAP and the other from Planck. And as you can see in this plot, over the last 20 years or so, the measurement of tau, while it's fluctuated a little bit, has largely decreased monotonically. And so that's an interesting trend. And one of the main insights or things that we want to emphasize in this talk is that the optical depth that you infer from the CMB is negatively correlated with the matter fraction that you get from the CMB. So by this, I mean that if you remove the large scale polarization data, and I just infer the matter fraction from the high L, meaning L greater than 30 or so, primary CMB along with CMB lensing, if my reionization bump at larger scales happen to be larger, then I would infer a lower matter fraction from the rest of the CMB data. And that has some interesting consequences that Gerrit will now get into.
So before we can get into what the implications of a different value of tau are, we should probably answer the question of what is a reasonable value of tau to look at. And as Noah has just pointed out, the primary CMB plus CMB lensing constrains some combination of tau and omega matter. By adding BAO data, we can break this degeneracy because BAO constrains primarily omega matter. This is nothing new. Previous works have looked at this inferred value of tau. What is new, however, is that this tension which has been showing up between the primary CMB and BAO now manifests as a tension between the low L inferred tau value and the high L tau value that we're getting in combination with CMB lensing and BAO. So you can see this here on the right. The purple curve is the tau that we're inferring from primary CMB high L plus CMB lensing and BAO, and in orange we're adding the low L CMB. And given that these two data sets are highly correlated, this corresponds to a 3 sigma tension between the high L inferred value and the low L Planck value. Coincidentally, the value that we're inferring from high L is perfectly consistent with what WMAP preferred prior to about 2015. That was sort of the accepted value of tau. And when we're now considering this higher value of tau, tau equals 0.09, and we replace the low L polarization likelihood with a simple Gaussian prior on tau, we can restore lambda CDM concordance. What you can see here on the right is that the CMB contours in this omega matter H0 RD plane move quite dramatically towards the DESI constraints, which are shown here in blue. This now corresponds to a consistent results at 0.9 sigma rather than the several sigma discrepancy that we found for a lower value of tau. As Noah had also mentioned, the preference for different matter fractions from the primary CMB and from BAO also manifested as a preference for subminimal neutrino masses or even negative neutrino masses. And you can see this here by extending the neutrino mass to negative values, simply extrapolating across zero. You can see that for a low value of tau, either by including the low LCMB likelihood or a Gaussian prior on tau equals 0.06, we have a strong preference for negative neutrino masses, which is clearly unphysical. However, when we're going to tau equals 0.09, we're getting this black curve, which is perfectly consistent with minimum mass normal hierarchy neutrinos, again at about 0.9 sigma. Incidentally, it's also consistent with inverted hierarchy neutrinos, should be somewhere around here.
Beyond just negative neutrino masses within lambda CDM, we can go ahead and look now at extended models, such as these dynamical dark energy models. And here in this plot, we're showing the constraints on this W0 WA parameterization, where again, we've substituted the large-scale polarization likelihood in the CMB with the Gaussian prior on the optical depth centered at either 0.06 or 0.09. So this pink contour here with tau of 0.06 is roughly similar to what you would expect from just including the low L EE likelihood as is in the Planck data. And so sure enough, when we do this, we find somewhere around a 3 sigma preference for W0 WA over lambda CDM, which is over here. Okay, so this is consistent with the stock DESI results. However, if we increase the optical depth to 0.09, now the matter fraction that you get from the CMB and the BAO data agree with one another, and so now your preference for W0 WA shrinks significantly down from 3 sigma or so to just 1.5 sigma. A similar story holds for other extensions to the vanilla lambda CDM model. This is true, for example, for the curvature fraction that one would infer from a joint analysis of DESI and CMB. Again, in pink, we're showing the results with a Planck-like value of tau of 0.06, for which a non-zero curvature fraction is favored by over 2 sigma or so. Whereas if I replace the low L likelihood with a larger value of tau of 0.09, this preference again decreases from 2.5 sigma or so to less than 2 sigma. And we'll note that while we haven't explicitly checked this for other proposed extensions, such as early dark energy, presumably the story would be the same there as well.
So what does a tau equals 0.09 universe look like? Well, the answer is lambda CDM is alive and well. And apart from omega matter and the primordial amplitude, the changes really are very minor. There's a small increase in H naught to about 68 kilometers per second per megaparsec, but nowhere near enough to resolve the H naught tension. NS also slightly increases to about 0.97, but again, no dramatic changes. Something else we wanted to highlight is that we don't need to actually go all the way to tau equals 0.09. A tau of as low as 0.08 would be sufficient to suppress all preferences for new physics below around 2 sigma. Now, is it possible that reionization could be very different from what we thought? And in fact, we have seen some evidence for that. JWST finds evidence for a much earlier onset of reionization by showing that there's Lyman alpha emission around redshift 13, as you can see in this figure. But Planck alone says reionization might be different, but tau is not. The standard CMB analysis assumes a hyperbolic tangent model for reionization, where there's basically just two parameters, the midpoint and the duration of reionization. But it's been shown that adopting a much more flexible reionization model leads to some freedom in the reionization history that's allowed by Planck, but it doesn't actually change the value of tau that's inferred from the primary CMB. And insofar, the low LCMB data is not compatible with any reionization history that accommodates such a large value of tau. Nevertheless, it's interesting to also think about what if there are some systematics and we might need to utilize alternative reionization constraints. So what other information do we have? Well, one important piece of the puzzle are quasars, which show us that reionization ends between about redshift 5.3 and 5.8. And by end here, we mean that the neutral fraction falls below 5%, and the universe is henceforth almost entirely ionized. It's been shown that with this information, a higher value of tau also implies a longer duration of reionization, because in order to achieve the larger value of tau while also having the endpoint of reionization fall into this very narrow redshift range, the only way you can do this is by extending the duration of reionization. And the duration of reionization is probed pretty well by the patchy KSE, which is inverse Compton scattering during reionization. And at face value, a larger value of tau and the late end of reionization are in some tension with those patchy KSE constraints. However, these constraints are pretty highly model dependent. As you can see here, the KSE signal, and here this includes both the reionization KSE as well as the late time KSE, contributes only a pretty small fraction of the total signal. But hopefully with future data, we'll be able to say more definitively whether such a difference is compatible with these constraints. And that brings me to what are we going to say in the future about such modifications? Are we going to be able to tell these models apart? And similarly to the work that pointed out the curvature as a possible alternative to evolving dark energy to accommodate the BAO data, it's possible that high redshift surveys will be able to tell the difference simply by leveraging the fact that at higher redshifts, the evolutions of different models will look slightly differently. The alternative for our specific suggestion is 4-point function constraints on the amplitude of the KSE signal. These are less model dependent than the work that I was showing on the previous slide. And so there's a possibility that these would constrain at least dramatic changes to reionization. Similarly, we could use CM 21 centimeter observations, but ultimately to really tell whether there may be a systematic, it may take new low L polarization measurements, for example, from a future LightBird mission.